And first of all, I would like to thank all the organizers for the very nice conference and for their kind invitation. And today's talk is about ranking from pairwise comparison data. This is a joint work with my PhD student, Pinghan Chen, and my co-author, Anders Zhang, who is currently an assistant professor at Wharton. So I would like to start the talk by discussing some of the most important applications of ranking, just to get you interested in this area. For example, in competitive sports, we need to rank teams or players according to the games played between two teams or two players. And in web search, we need to develop an algorithm to rank web pages according to their relevance to search words, for example. And another important example is recommendation system. When you do shopping on Amazon, the website will sometimes recommend items and hope you will click items and eventually purchase the product. And this is usually done according to a rank of all products based on your personal interest and especially your personal purchase history. Another cost-effective way Amazon does is to show you just several items each time, and then they can find out which item you prefer, depending on which item you click. And the rank of all the products can be estimated once enough comparison data is collected. So statistically, the problem of ranking can be formulated as the famous Bradley-Terry-Luce model. At least this is one of the simplest formulation, and we are going to focus on the BTL model in today's talk. So imagine we have n players, and what we want to do is to rank the n players according to their skills or the abilities. Okay, so in this framework, we are going to model the outcome of a game played between I and J by a Bernoulli distribution with probability that is proportional to the exponential of the skill parameter of the players. For example, the probability that I will win the game against player J is proportional to e to the power of theta I, and vice versa. So basically what we have here is a logistic transformation of the difference between the skill parameters of the two players. Okay, so here's the simple sampling scheme that I'm going to consider in this talk. So instead of observing comparison or games played between all pairs, let's assume we can only observe a very small subset of the comparison results. This is modeled by an Erdo-Shreni random graph, and for each pair I and J, whether they are compared is determined by a random event with probability P, right? So Aij is the indicator whether there is an edge connecting I and J, the adjacency matrix of the Erdo-Shreni graph. So as long as Aij equals 1, there will be a capital L independent games played between player I and player J, and the results of the game are denoted by Y sub IJL, okay? So here, the small l is ranged from 1 to capital L. So as long as there is an edge between two players, we will have a capital L number of games played between them. And our hope is to study a random graph that is as sparse as possible. However, we cannot let the probability P to be arbitrarily small. We need to assume that the probability P to be at least of order log n over n throughout the talk. For those of you who are familiar with random graph theory, this is actually the necessary and sufficient condition for a random graph to be connected. So it only has a single component, connected component. Okay, so if this is because if P is of a smaller order than log n over n, the graph will have several disconnected components, meaning it will be impossible to rank the players according to because of the lack of the comparisons. So I hope the model setting is clear to you. In the literature of ranking, there are basically two. In this talks, I would like to discuss two ranking problems. The first one is called top K ranking. This is today's topic, and the goal of top K ranking is to find the K best players from the data. Okay, so this is the focus of today's talk. And in my second talk, I will discuss the problem of full ranking, which is to find the whole ranking result of all players. And we are going to focus on the first problem today. Okay, so this is our setting. I hope it makes sense. In the literature of ranking, there are basically two popular methods. And let me introduce these two methods. The first method is the maximum likelihood estimator. As the name suggests, you just compute the MLE of the data. This will give you an estimator for the skill parameter, and then you can rank the players according to the values of the skill parameters. Right? So it has three straightforward steps. In the first step, we can compute the average of those YIJL for each pair. Okay, so this number is the summary statistic that can be understood as the win ratio for player I against player J, and this is our sufficient statistic according to the Bernoulli model. And then we can write down the negative log likelihood function, and the maximum likelihood estimator is the minimizer of this function. Right? So once we obtain the estimator from the data, we can then rank theta. We can then rank theta hat and obtain the top K ranking result. So the computation of the maximum likelihood estimator is straightforward. This is just a logistic regression, a convex problem, so it can be implemented by algorithms such as gradient descent. Now, the second algorithm I would like to talk about is slightly more complicated, but I will give you some intuition later to understand this algorithm. So this is known as the spectral method. This is introduced by Negaban, O, and Chao back in 2017. This is from the MIT group. It is also known as the rank centrality algorithm in the literature. If you know PageRank, this is very similar to the PageRank algorithm that is used by Google for web search. So in the first step of the algorithm, we compute a matrix, P. So the matrix P is defined as follows. So for the off-diagonal entry, it is the product of Aij and Yji bar divided by some number D. I will tell you what D is later. And then for the diagonal entries, it is just whatever make sure each column of the matrix P sums up to 1, okay? And you are going to choose this number D to make sure each entry Pij is a number that is ranged between 0 and 1, so can be interpreted as a probability. Therefore, by the definition, this matrix is a Markov transition matrix, right? So the second step, you can compute the stationary distribution. Let's call it pi hat. The stationary distribution of the Markov transition matrix is pi hat. It is an n-dimensional vector, and then we can rank all the players according to the n entries of the stationary distribution. Okay, so we can obtain the top K ranking result. So the spectral algorithm definitely looks quite strange because it is not like the maximum likelihood estimator, whose meaning is very clear and straightforward. The MLE simply estimates the skill parameter and then rank the players according to the skills. So why is the stationary distribution here of some Markov chain related to the skill of the player, right? So, well, we can actually compute the conditional expectation of the transition matrix. And this leads to the population version of the Markov chain. And then we can define a probability vector pi in this way. Each entry of pi is proportional to the exponential of the skill parameter of each player. Okay, and it is easy to check that pi transpose the conditional expectation of the sample version of the transition matrix equals pi transpose. So this pi is indeed the stationary distribution of the population version of the Markov transition matrix, right? So according to the definition of pi, obviously ranking players using pi is equivalent to ranking players using theta, which is the scale of the player. This is how the algorithm works, right? The spectral method can be understood as an estimator of the Markov chain from the data. Okay, so now let me tell you about the literature in this area. So there are lots of paper written in this area discuss the optimal algorithms in top K ranking. Most of the paper are written in the setting of the BTL model. To the best of my knowledge, the state-of-the-art result is given by this paper by the Princeton group. It appears last year, 2019, on Annals of Statistics by Yuxing Chen, Jianqing Fan, and their co-authors. So as the title of the paper suggests, what they are able to show is both the spectral method and the maximum likelihood estimator are optimal. Okay, so this result is unknown before the paper. Previously, people know that you have to combine the two methods to do optimal top K ranking, but they are able to show you can actually use either a spectral method alone or MLE alone to achieve optimal top K ranking. So let me briefly summarize this result in the literature. But first of all, let me introduce some of the assumption that is adopted in the paper. This is also the assumption that I'm going to talk about for our result. So without loss of generality, first of all, let's assume that the scale parameters are ordered from the largest value to the smallest value, okay? So theta1 is the scale parameter of the top player, and theta2 is the parameter of the second best, and so on and so forth. Okay, so we have this is theta, and our goal is to estimate the best K players. Therefore, it is necessary to assume there is a gap between the ability or the skills of the K's player and the K+1's player. Okay, so we assume there is a parameter called the separation parameter delta that separates the skills between the K's player and the K+1's player. So this is the first parameter that we in the assumption. The second parameter is kappa. It is called dynamic range that controls the range of the ability of the player, right? So it is simply defined as an upper bound of the difference between the strongest player and the weakest player, right? So theta1 minus theta n is bounded by this kappa. Okay, so the larger the dynamic range, the more diverse the group of the people. Okay, and we will see how kappa is going to affect the optimal top K ranking problem. And throughout the talk, I'm going to assume that kappa is a constant order. Okay, all right. So the first result in this paper by Cheng et al. 2019 is the following result. So as long as the signal separation parameter delta squared is greater than this ratio log n over MPL up to a constant C1, then both the spectral algorithm and the maximum likelihood estimator is able to find the top K set with a high probability, right? So this is the exact recovery result. If this is true, then you can recover the top K players from the data without any error. Okay, so this ratio log n over MPL is not very hard to understand. The numerator log n is just a consequence from the union bound, and the denominator MPL can be understood as the effective sample size of each player, right? So L, remember L is the number of L is the number of games played between each pair of players, and for each player, its expected degree in the random graph is MP. Okay, so MPL is the expected number of games played by each player. So that's why it's called the effective sample size. And not only that, the second result of that paper shows that this condition is optimal in the sense that if the separation parameters delta squared is smaller than this number up to some small constant C2, then no algorithm is able to find the top K set with high probability. In a sense, this result is sharp, at least in terms of the rate, and not necessarily the constant. Okay. I also want to emphasize that they actually provide the third result, which I want to present here. The third result is not a theoretical result; it's a very interesting numerical experiment. In the paper, they are able to conduct a very simple numerical experiment for the following setting. This is actually the simplest setting you can think of, just a two-group setting. Assume the scale parameter is a piecewise constant vector. You only have two pieces, right? So the top K group, people all have a scale parameter delta, and the remaining players have scales 0. Okay, so in this case, both the dynamic range and the separation parameter is This is the result. They apply both the maximum likelihood estimator and the spectral algorithm, and then they plot the success probability as a function against the separation parameter delta, right? So as you can see, as delta grows from 0 to infinity, you can clearly see a phase transition for these algorithms, right? So the success probability increased to 1 very fast. And moreover, what is interesting is that the curves really overlaps. Okay, so it's basically you can conclude that the performance of the two methods are the same, right? So the theory tell you both the algorithms are optimal up to a constant, but the result may suggest maybe even the constants are the same. So our question is this actually true, right? So are the two methods identical up to a constant? And this is something that we want to tackle. So this is our result. So the first result that we can show is, okay, so the maximum likelihood estimator for top K ranking under the BTL model is indeed optimal. But here, by optimality, what we mean is a stronger notion of optimality. I will tell you that later. But moreover, the second result comes as a little surprise to us. The spectral method is actually not optimal, okay? Well, here, not optimal, I mean the constant is not sharp, despite that the rate is optimal, right? And the result 3, we are able to find explanation for the interesting simulation result in the paper. The simulation setting in the paper by Chao et al. Is actually the only setting that you can show a spectral method is optimal, and they are lucky to find the setting. You know, it's actually natural because this is the simplest setting that you can think of. Okay, so now let me before I talk in detail about our results, I would like to introduce two variance functions. So remember, kappa, the parameter kappa has the meaning of the dynamic range, right? It's defined as the upper bound of the difference of the strongest player minus the weakest player. Okay, so here we have a function of kappa. We call it a variance function. It is defined in this way. So for each kappa, you can define this optimization problem, solve it, you get the value of v of kappa, right? So it defines a function. Now the definition looks slightly complicated, but it's not important. What is important is that it's a function of kappa. Later, I will show you the picture of this function, and I will also talk about the property of this function. So this is the first variance function. Another function I call v bar kappa is also defined through optimization. And using these two functions, we are able to state our result. So this is our first result for the maximum likelihood estimator. We are able to show if the separation parameter delta squared is greater than 2 times the variance function times this ratio of log n over MPL, then the maximum likelihood estimator is able to recover the top K set with high probability, right? So this result does not contradict the result of Chao et al. It has the same rate, log n over MPL, but we are able to say more about the leading constant, right? The correct constant of the condition is determined by 2 times the variance function that appears in the previous slide. So it tells you exactly how the dynamic range affects the difficulty of the top K ranking problem. Now, for this ratio, you can see the denominator is still MPL, so it's the same effective sample size, but the numerator is more precise. It is of the form, it is written as the square of root log K plus root log m minus K, right? So you can see there is a symmetry between K and m minus K. This is easy to understand because mathematically, the problem of top K ranking and the bottom K ranking are the same, right? So that's why you see this symmetry between K and m minus K. And we are also able to show that this condition is actually optimal if delta square is smaller than 2 times this variance function times this ratio, then no algorithm works. Okay, so the maximum likelihood estimator is exactly the optimal condition, the optimal algorithm for top K ranking, not only for the rate, but also the leading constant is correct. The second result is for the spectral method. the condition it requires is the same as the maximum likelihood estimator, except here we need a different variance function, right? So instead of using V, we use V bar, which means spectral method has a different leading constant. That's why it's not optimal if you consider the effect of the leading constant. And moreover, if this condition is not satisfied, then spectral method fails, right? So 2 times V bar of kappa is the exact leading constant for spectral method. Okay, so now with these 2 results, if you want to compare the 2 most popular algorithms of top K ranking in the literature, the MLE and the spectral method, you only need to compare the 2 leading constant, which is determined by the 2 variance functions. And let's actually do that. So this lemma tells you the properties of these 2 variance functions. First of all, both variance functions are increasing functions in terms of the dynamic range. So if kappa increase, the group of people become more diverse, then you have a higher variance. The problem of top K ranking becomes harder. That's the message. And moreover, the variance function V bar is always greater than or equal to the variance function of V. This means the spectral algorithm has a higher variance than the maximum likelihood estimator for any dynamic range kappa. And the only case that the 2 variance functions are the same is when kappa equals 0. Okay, so here, let me show you some of the plots. We actually plot these 2 variance functions. As you can see in the picture, both are increasing functions. The blue one is the variance function of the maximum likelihood estimator, which is always below the orange function, which is the variance function of the spectral algorithm. And we plot the 2 functions with different choices of K over N, and you can see how that affects the shape of the counter function as well. Now, what's the difference between the top 3 plots versus the bottom 3 plots? Well, actually, they are the same plots. The top 3 plots are plotted against the standard y-axis, but the y-axis in the bottom 3 plots are plotted in a logarithmic scale. Okay, so if you look at the bottom 3 functions plots, you can conclude that actually both V and the V bar not only are increasing, but they increase as kappa grows at an exponential speed. Okay, not only that, but the difference between V bar and the V is an exponentially increasing function with respect to kappa. So as kappa grows, the difference between V bar and V is very large. It grows to infinity exponentially. That will significantly affect the performance of practice of these algorithms. Okay, so now I want to explain why in Cheng et al.'s paper, they show this numerical result, which demonstrates that the 2 algorithms have the same numerical performance in practice. Okay, and remember here we have 2 parameters. Delta is the separation parameter, and kappa is the dynamic range. And the previous lemma tells you that the 2 variance functions are the same if and only if kappa equals 0. And another consequence of this result is they are equivalent as long as kappa goes to 0, right? So the only situation where the ratio of the 2 variance functions tends to 1 is when kappa goes to 0, right? And the special case of this scenario is exactly the simulation setting considered by their paper, right? So if you look at this 2-group setting, okay, so because it has only 2 groups, so in this case, the dynamic range parameter kappa equals delta, right? So when kappa goes to 0, delta also goes to 0, right? So when delta goes to 0, kappa also goes to 0. This is why you have the equivalence of the 2 variance function, and therefore the performance of the 2 algorithms should be the same. If delta does not go to 0, delta is a constant, then according to our previous 2 lemmas, you look at the upper bound, then the upper bound conditions of the both algorithms are satisfied. Okay, so you can actually predict that in this 2-group structure case, the 2 algorithms should have the same performance, and this is actually essentially the only case where the 2 algorithms are the same. Let me actually show you more experiments to move beyond the setting of the 2-group structure. Okay. First of all, we are able to replicate their results, right? So in this case, the 2 algorithms indeed have the same performance. Now let's consider another setting, n equals 200 and k equals 50. This is the top 50 ranking problem. And let's consider a more complicated structure. This is a 4-group structure, right? So in the top 50 group, we further divide the top 50 group by 2 subgroups, right? So from player 1 to 25, they have scales 10. And then from 26 to 50, they have scales 10 minus tau. And from 51 to 100, it has scales 10 minus tau minus delta, right? So in this case, the gap between the 2 group is a delta, right? Delta is still the separation parameter. And the last group, 101 to 200, all have scales 0. Okay, and we are going to set the value of tau to be 1, for example. And you can see if we vary delta from 0 to infinity, there is a clear difference between the 2 methods, right? As I just said, the difference of the 2 variance function is an exponential function with respect to kappa. In this case, kappa equals 10, so the difference is really large, right? So this is another result for tau equals 4. You can again see the difference between the 2 methods. It's very obvious. And another setting is more complicated, right? So we sample the first 50 players from the uniform distribution ranged between 6 and 10. And the remaining players are sampled from 0 to 6 minus delta. And again, in this case, delta is the separation parameter, right? And we run MLE and a spectral method. And again, MLE systematically dominates the performance of the spectral method, right? So the only case that you can find the 2 methods are the same is the 2-group structure, which is the dissemination result in Chen and O's paper. Okay, so now I want to tell you about the dynamic range, the influence of the dynamic range in top K ranking problem, right? As the picture shows, both variance functions are increasing function of the dynamic range parameter, which means the larger the kappa, the harder the top K ranking problem is. But the question is, why is that, right? So when we first try to think of that, it's not very intuitive, but later we are convinced by the following very simple toy example. So let me try to explain what's going on here. Okay, so this is a toy example. We only have 3 players, and we just want to find the best player among the 3 players, right? The top 1 ranking problem among 3 players. And let's assume there are edge between 1 and 3, 2 and 3, but no edge between 1 and 2. Okay, so this is the graph setting. And let's consider the following 2 scenarios, right? So in the first scenario, the best player has scale 1, then the other 2 has scale 0. And in the second scenario, right, the best player has scale 1, the second has 0. But the third player is so weak, he has a scale -1,000, just to make things a little bit more extreme, okay? Now, the question I have for you is, in which scenario is top K ranking easier? Okay, maybe I'll give you 10 seconds to think about that. Okay, so the answer is actually the first scenario is a simpler problem. So let me explain why, right? So we want to find the best player among the 3 players. There is no link between 1 and 2, right? There are no games played between 1 and 2, so you cannot make direct comparison. The comparison between 1 and 2 has to be made through player 3, okay? So you have to compare the records of the games played against the same player, which is player 3, okay? So let's look at the first scenario. Player 2 and the player 3 have the same skills. So let's say you have 10 games played between 2 and 3, so player 2 will win about 50% of the game, right? In expectation, it's 5 games. But player 1, since it has skills 1, right? Theta 1 minus theta 2 is 1, it's positive. So maybe player 1 will win majority of the games, right? So from that comparison, you can conclude player 1 is the best player. However, you cannot make that conclusion in the second scenario, because in the second scenario, player 3 is so weak, he is going to lose all the games against both player 1 and the player 2, right? So player 1 and player 2, both of them will have 100% win record against player 3. You cannot conclude which player is the better player. There is no information data because of the large dynamic range parameter. So a large dynamic range parameter, in the worst case, is going to make the top tier ranking problem hard. Okay, so now let me just make some conclusions before I go to the analysis. So first of all, both the maximum likelihood estimator and the spectral algorithm are rate optimal. However, the constants before the rates are different. MLE has an optimal constant, but spectral algorithm, in general, the constant is not optimal. So now I want to talk about the analysis, how we are able to establish the result, basically the idea behind the proof. Let me first make the problem more general by talking about the decision theory that we have for the ranking problem. So let's first introduce an object called R. R is a permutation vector or a rank vector. So what it means is it is a vector of length dimension n. So Ri equals j, it means player I is ranked at the j's position. Okay, so with R, the mathematical problem of ranking is clear. All we want to do is to estimate this permutation vector. Okay, so now the top k set is defined to be the collection of players whose rank is below or equal to k. Okay, so if you have an estimator of the rank, let's say R hat, then you can estimate the top k set by k hat. Okay, so the next we will define the loss function to measure the difference between the two sets. So basically, this is the Hamming distance, the normalized Hamming distance that measures the type 1 and type 2 error. It can also be think of as the symmetric difference between the two sets, k hat and k. Okay, so it is 1 over 2k. This is the normalization factor that we need times what is in the parentheses. So what appears in the parentheses is the type 1 error and the type 2 error for the problem, right? So you can really think of the top k ranking problem as a variable selection problem, right? It's basically variable selection. In variable selection, you want to select important variables. In top k ranking, you want to select important players. So it's the same thing mathematically. And for variable selection, we have we have type 1 error. This is false positive and also false negative, which contributes to the two terms in the error in the loss function. The reason we normalize the loss by 1 over 2k is to make sure this loss is ranged between 0 and 1. So when we compute the minimax rate, it has a nice form. Okay, so the property that we have for these loss functions is that it exactly characterizes what we want. So the loss is 0 if and only if you are able to exactly recover the top k set. Okay. Now, with this loss function, we are able to study a more general problem than exact recovery, right? So we are able to study what is called the partial recovery. We say we have partial recovery or weak consistency if the loss function goes to 0. And then exact recovery is a special case. It's just when the loss function exactly equals 0. It is also called the strong consistency in the literature, right? So in the literature of top k ranking, to the best of my knowledge, no one has ever considered the problem of partial recovery. All the results are about exact recovery, but I think in practice this is not very realistic because the real data is noisy, so you always expect to make some mistakes. So the study of partial recovery is more relevant in practice, right? So moreover, we don't need to study exact recovery. This is because the following relation, right? So there is equivalence between exact recovery and a partial recovery by this relation. So the loss function is 0 if and only if the loss is below the threshold 1 over 2k. This is a simple consequence of the definition of the loss, right? So the loss is defined as 1 over 2k times the sum of some indicator functions. And because of that, the loss function can only take value on the grid, right? So it can only take 0. The next value it can take is 1 over 2k. The next one is 2 over 2k, 3 over 2k, 4 over 2k, so on and so forth, right? So as long as the loss is below 1 over 2k, the only value it can take is 0. That's why you have the equivalence. Okay, so I would like to say this framework of study the top K ranking problem from a decision theoretic perspective is totally inspired by the previous work in variable selection. So I would like to mention the paper by Christina and his co-authors in 2018 that they study the variable selection problem in the Hamming distance. It's basically the same formulation, and our formulation of top K ranking exactly borrows this formulation. And later, Kendall and Tibakov has a paper that extends the result to the regression setting. Okay, and for the variable selection, what you have is also this normalized Hamming distance, right? Because it is just 1/2s, where s is the sparsity of the problem, and then times the sum of type 1 and type 2 error, and our loss function is the same form. Okay, so the first theorem that we have is the minimax rate of the problem, right? So with respect to the normalized Hamming distance, the minimax rate is an exponential function. What appears on the exponent is slightly complicated, but it involves a signal-to-noise ratio parameter and the sample size n and k, which is the definition of the problem. Okay, the signal-to-noise ratio parameter is equivalent to the ratio MPL times delta squared over the variance function, right? So on the denominator, you have the variance function that characterizes the noise level. On the numerator, you have MPL, which is the effective sample size times the separation parameter squared. Therefore, it is called the signal-to-noise ratio, right? So moreover, we are able to show the maximum likelihood estimator is able to achieve this rate. So MLE is not just optimal for exact recovery. It is also optimal for partial recovery. And the second result is for spectral algorithm. It has a similar form of exponential convergence rate, but for spectral algorithm, the signal-to-noise ratio parameter is defined slightly differently. So you just replace the variance function of MLE by V bar, which is the variance function of the spectral method. Okay, so I want to emphasize this rate is not just the upper bound for spectral algorithm. We also show it is the lower bound for spectral algorithm. Therefore, we can make a rigorous comparison between the two methods. And as I just said earlier, if you have a result for partial recovery, you immediately get the result for exact recovery by this relation, right? So what you can do is to take the minimax rate that you have, which is this exponential function, and make it below the threshold 1/2k, right? So this is the condition that you have for exact recovery. And if you rearrange this condition, you get exactly the same condition that we present in the previous theorem for the exact recovery condition. This is how we actually prove when MLE achieves the optimal exact recovery condition. And the same thing can be done for spectral algorithm as well. Okay, so this is our result. And now let's talk about the analysis. The first step of the analysis is this very basic inequality I would like to talk about. So suppose you have a rank vector R, and what you want to estimate R is by ordering the estimator of the scale parameter, right? So theta hat is the estimator of the scale parameter. Then R hat is the rank that is obtained by ordering the entries of theta hat. So the inequality that we can prove is the risk with respect to the normalized Hamming distance is bounded by 1/k times this term on the right-hand side. So this term appears on the right-hand side can be understood as the error of the oracle thresholding rule. So what is a thresholding rule? A thresholding rule is the following procedure. Now you have the estimator for the scale parameter theta hat. Then you estimate the top K set, the set of good players by thresholding, right? So whenever theta hat I is greater than T, this is your threshold level, then player I is considered to be a strong player, right? It is classified in the top K in the top set. Otherwise, it is classified in the as the bottom set. Okay, and basically what you have on the right-hand side is the type 1 error plus the type 2 error for the thresholding rule. Not only that, we can actually put a minimum over t in front of the sum of the two terms. So this is actually the error of the oracle thresholding rule, right? So this inequality is very helpful. Because of that, we do not need to exactly analyze the permutation vectors, right? So we can the analysis is now reduced to the analysis of the tail probability of the maximum likelihood estimator. As long as you can exactly characterize the tail of each entry of theta hat, then you can find the minimax rate by upper bound the tail probability. And this is what we are going to do. Okay, so let's talk about the maximum likelihood estimator first. And without loss of generality, let's talk about the first entry of the maximum likelihood estimator. Okay, so the MLE is defined to be the minimizer of the negative log likelihood function. So first of all, by a simple Taylor expansion, you can write down this expansion at least formally for the first entry of theta for the MLE, right? So the first entry of theta hat equals theta, which is the true parameter, minus a leading term, and then plus whatever is considered as a remainder. Okay, so the leading term will contribute, will characterize the behavior, will determine the behavior of the tail probability of the difference, right? So this is the main term we want to understand. But what is difficult is the analysis of this term. How we are going to do that, right? So let's look at the numerator of this term. The numerator of this term is the sum of a product. It's the product of A1j times y bar 1j minus the mean, but the mean that is evaluated at the maximum likelihood estimator. Okay, so at least there are two challenges. The first challenge is that the mean function is not evaluated at the truth, but at the maximum likelihood estimator. Okay, so if only we can replace this by the true version of the mean function, then it'll be great, right? But that requires a global control of the error vector of theta hat, right? To be specific, we need to control theta hat minus theta in terms of both L2 loss and L infinity loss. This is what we need to tackle the first challenge. Now, the second challenge is the product appears in the numerator is this form, but as you can see, there is dependence between A1j and theta hat 1 and theta hat j, right? So without this dependence, we can just apply Bernstein inequality or whatever large deviation inequality that you like to bound the tail probability with the correct constant. But because of this dependence, we cannot do that. So this is the second challenge, and we are going to address that as well, right? So for the first challenge, this is the problem, right? So we have to prove a global error control of the maximum likelihood estimator, but that relies on the smallest eigenvalue of the Hessian matrix of the log likelihood function, right? Because the Hessian determines the identifiability of such an estimator. However, the Hessian matrix is problematic, right? So let me write down the definition of the Hessian matrix. It has a simple form. The off-diagonal entry is the product of these two terms, and the diagonal entry is the sum of these terms. If you are familiar with random graph theory, then you may recognize this is actually the graph Laplacian of some weighted random graph, but this is not important. What is important is if you look at this term, this is the derivative of the sigmoid function, right? So the sigmoid function has a derivative that can be exponentially small depending on the value of its argument, right? So if this term, which is the difference between theta I and theta j, is very large, then this value is going to be exponentially small. As a consequence, the smallest eigenvalue is going to be exponentially small. So you cannot control a global error for the maximum likelihood estimator. Well, the good news is at least we can control the Hessian at the truth, because we have assumed that the difference is bound by the dynamic range parameter, and we assume the dynamic range parameter is of constant order, right? but we can only control the Hessian at the truth. This is not enough. What we need is the control of Hessian at some point which is in the middle of the truth and the maximum likelihood estimator, right? So we have to control Hessian at some random point beyond the truth. This is why we lose this control, right? So how we are going to address this problem is through the analysis of the gradient descent sequence. So here I want to emphasize that by writing down the gradient descent algorithm, we are not going to use that for algorithm in the practice, but we are going to use this algorithm in the proof. So this is the idea, okay? So the idea is if we can control the global error of the gradient descent step at each iteration, then by the convexity of the objective function, the gradient descent sequence will converge to the global optimizer, which is the maximum likelihood estimator. If we can control that at each step, eventually we can control the maximum likelihood estimator, right? So the good news is to control the global error of theta t plus 1, the gradient descent step at t plus 1 step, it only depends on the Hessian at the previous step, right? So this is very important. This is good news. It comes from a standard analysis of gradient descent. Okay, so now we can just initialize the gradient descent sequence at truth, right? Remember, we are not going to use this algorithm in practice. We only use this algorithm in the proof, so we can initialize wherever we want. So initialize the algorithm at truth. At least we can control the Hessian at truth. Therefore, we can control the Hessian at initialization, and therefore we can control the global error of the gradient descent step at the first step, right? We can control theta 1. Now, if we can control theta 1, as a consequence, we can also control the Hessian of theta 1, right? If we can control the Hessian at theta 1, we can then have a global error control of theta 2. Okay, so it just by using a mathematical induction argument, we can apply this idea to find the global error control for the maximum likelihood estimator. Okay, this is how we address the first challenge. Now, for the second challenge, it's a little bit more complicated. This relies on what is called a leave-in out trick. I think at this point, this trick is now well known. In my opinion, this is probably one of the most important tricks that is developed in the last 3 years in high-dimensional analysis. It's very important. If you know that, you can analyze lots of the problems that cannot be analyzed before. Okay, so the idea is we are going to define a perturbation of the likelihood of the maximum likelihood estimator by leave the first row out, right? Remember, our data can be organized into a matrix. We just remove the first row. This is the games played by the first player, right? We just remove all the games played by that involves player 1. And this gives us a leaving out version of the maximum likelihood estimator. And then we expand this product as the telescoping this expansion. Now let's look at these two terms, right? For the first term, we already have independence by definition, because the definition of the leaving out version of the maximum likelihood estimator does not depend on first row of data. It is going to be independent of these quantities, okay? Therefore, we have independence. We can apply Bernstein inequality directly for the sum of these things, right? So for the second term, it's going to be small because the leaving out version of the MLE is just small perturbation, right? It only removes the one row among all the n rows. So this is the idea. If you combine these two ideas, then you are able to analyze each entry of the MLE and characterize exactly the tail behavior. So here, this is a very nice paper written by, again, this is the Princeton group. And I think Yuxin Chen is the main player in this area that promotes the idea of leaving out. And you can really use this idea to analyze not only algorithm, but also statistical property of many convex and non-convex statistical estimation problems, including phase retrieval, matrix completion, and today you see a ranking under the BTL model. Okay, so the analysis of the spectral algorithms is similar. Let me briefly go through that. So we just start by the definition of the spectral algorithm, right? So remember what we have is pi hat. It is this stationary distribution of a Markov transition matrix. So we have this identity, right? So it's identity of an n-dimensional vector. So if you unpack that, this will give you n equations. Let's just take the first equation. The first equation can be rearranged into this form, right? This expansion is actually exact if you choose this pi bar property. I didn't tell you what pi bar is, but you can define this pi bar as long as this equation is satisfied. It's straightforward. But now, what is important is the analysis of this term. Okay, and again, we can use this leaving out idea. We are going to define a perturbed version of the stationary distribution. This is by removing the first row and the first column of the Markov transition matrix, and this will give you a leaving out version of the stationary distribution, right? And again, for this first term, it is very close, very small, because it's just a leaving out, a small perturbation. And the second term, you have independence. Then you can apply Bernstein inequality for the second term, and then understand the tail behavior of this guy. Okay, so in summary, if you go through the previous analysis, basically what you can show is that the leading contribution of the difference vector of the maximum likelihood estimator is given by this guy, right? So this guy is very clean. You can easily analyze or understand its tail behavior. And on the other hand, for spectral method, the leading expansion after the leaving out analysis has this form. Okay, so now we can directly compare the two stochastic error terms that appear in the expansion of the maximum likelihood estimator and the stationary distribution estimator. Okay, so intuitively, what you can argue, this is actually not rigorous. This notation, is a non-rigorous notation. It means the tail behavior of this quantity is basically the same tail behavior of this Gaussian distribution in the worst case. Okay, so in the worst case, the tail behavior of this error term is given by the Gaussian distribution with mean 0, variance given by V over NPL, and in comparison, the tail behavior of this guy, this is from the spectral method, and in the worst case, is determined by this Gaussian distribution with a different variance function, right? So now you can directly see why the two methods are the same. Basically, the variance of the spectral method is not optimal. Okay, and moreover, you can also understand why the maximum likelihood estimator is optimal, because this guy is exactly the worst case inverse Fisher formation. That's why it is optimal. Of course, our proved lower bound is not based on Fisher formation, but based on a hypothesis testing argument. But at least this intuitively tells you why the maximum likelihood is optimal. Okay, so this is my last slide. So to conclude my talk, I want to give some comments on the optimality of the spectral method. Right. So spectral method is a very common idea used in high-dimensional statistics, usually for very complex model like mixture model or stochastic model. Okay, and people have been understanding spectral methods for a long time, and I think up to this point we have a very good understanding of spectral method. We are able to analyze spectral method very accurately. For example, we have these two recent papers. The first one is by Matthias and Anderson and Harry. They showed that for Gaussian mixture model, if you apply a spectral algorithm, you can actually achieve the minimax rate of clustering. Not only that, the minimax rate has an exponential rate. The exponent is exact, right? So the spectral method is going to achieve the exact exponent. This means if you want exact recovery, not just the rate is optimal, the constant of spectral method is also optimal. Okay, the same phenomenon is also true for stochastic block model. Right, this paper by Emmanuel Abbey, Gentry-Fine, and co-authors, they showed that spectral clustering in stochastic model has the same optimality property, and for exact recovery, the leading constant is also optimal, not just the rate. Right, so these two papers actually provide people with confidence and actually evidence that we tend to believe the spectral method can replace maximum likelihood estimate. It's optimal, but actually we are able to show in the example of top-tier ranking, this is not the case, right? For top-tier ranking, spectral method is not optimal. This actually comes as a surprise to us because after we learned these two papers, we thought for a long time that spectral method is optimal, but it's not. Now, the next question is there a general phenomenon or a general rule that we can say when and why spectral method is optimal or not? Unfortunately, I don't know. I think at least to my current knowledge, this is really a case-by-case analysis, right? So my only advice is we need to be careful, right? So whenever we want to use spectral method, we need to make sure we have a careful and precise analysis to understand its behavior. Okay, so this is the last slide, and I want to thank you for the attention.
Okay, so Chao, thank you very much for a very nice presentation. So we have some time for questions. So I saw already one question in the chat. So Pavel, would you like to ask this question? I don't know whether I have to do something to unmute.
So I see a question by the audience in the chat.
Yeah.
Can I answer that?
I think you can answer, but so I mean there is also just hand up from Sasha. So please try to address first question by Pavel. So
okay. Okay. So the first question is the convergence of grid descent relies not on convexity but strong convexity. This is a very good question. Actually, this is actually true. We can show the object function is a strongly convex function with high probability. That's why you have the convergence.
Okay, so this is a right remark, yeah. Okay, then there is another wish of question by Sasha. So should I do something to?
I can speak now, probably. Yes?
Okay, please.
Hi, everyone. Hi, Chao.
Hi, Sasha.
It was a very interesting presentation, and you draw parallels with variable selection, classical variable selection problems. There is a difference between the conditions of partial recovery and exact recovery.
Okay.
So, in your case, I did not see this. So, could you explain it?
So the condition that we need for the partial recovery is the exponent of the rate goes to infinity. Basically, this is the condition when you can show the error goes to 0. This is the condition that we can prove a partial recovery. The exact recovery is the condition when the exponent is greater than log 2k.
Okay, so you just didn't mention this partial recovery.
I didn't mention that.
Okay. And another question, I didn't understand what is lower bound over all methods. So you mentioned the upper and lower bound for these two particular methods, but say the minimax constant.
The MLE lower bound is also the minimax lower bound.
I see. Mm-hmm. Okay,
but the lower bound for the spectral algorithm is just the lower bound for the spectral algorithm.
Mm-hmm. Okay, thank you.
So more questions, so maybe I ask my questions that people can still think about. So you presented the rates and sharp constants. So this somehow suggests that your melee has some limiting distribution. And you computed the variance of this limiting distribution. So is it, can you state the result about the asymptotic normality?
Yes, this is a very good question. What we show is what we can show is the probability tail of this guy is the probability tail of this guy, right? So basically, this guy greater than t has the same exponent than this guy greater than t. We actually wish we can show this actually converges in distribution to distribution, but we cannot show that now, right? So because if we can show that, then we can build confidence interval. We try very hard. This is actually something that we are working on, but it's very disappointing. There is some term in the error that we cannot eliminate. Actually, I'm not confident that I can show this result. But the simulation suggests that the result is definitely true. I believe the result is true for this guy converges to distribution and this converges to that, but I cannot prove that.
Okay, so maybe a related question. So all your observations are Bernoullis with different parameters.
Yes.
So
yeah.
Suggest to use the machinery or generalized linear models. Did you try in this way?
Generalized linear model.
Yeah.
Okay, I can definitely prove Gaussian. It's actually much easier than the Bernoulli observation, but I don't know how to analyze the other generalized linear model.
Okay, so maybe we can chat later. I have some ideas about this.
Oh, great. Yeah.
Good. So more questions?
Vladimir, I have a question if I can.
Hi, Richard.
Hi, Chao. Well done for waking up in time.
I have to.
So how would you expect the story to change if you didn't assume that kappa was bounded?
Oh, it's a very good question. So if kappa is not bounded, I don't think I can prove maximum likelihood estimator works, even though I believe in simulation it will still work. And in Friday's talk, I will talk about full ranking, which is to rank all the players, not just to find the top K place. In this talk, I'm going to assume a growing dynamic range, and I will present a technique called the divide and conquer algorithm. So basically, what we can do is to divide the players into several groups. Then in each group, you apply the maximum likelihood estimator, and that will give you optimal result. I think for top K ranking, that will address the problem as well, but we didn't do that.
Good, thanks.
Thank you.
I think so. We are a little bit out of time. We still need time for a short break. So I suggest that we stop now. We will still have an opportunity to ask Chao after the second lecture.